mathematician slash chemist that's trying to keep you updated on the latest happenings in science. So pretty much what I do is just browse the websites of top scientific journals, look at random papers, whatever jumps out to me and seems interesting, and I try to figure out what what the research is about by only looking at the figures, which people don't talk about very much, but scientists are very good at producing aesthetically pleasing figures. Not just if you're the kind of guy like me that likes to look at data, but also figures that just look nice in general. So I'm going to drop a quick message in the chat here, just in case anyone decides to join me later. For now, I'm just going to myself. So I try to do this. I just stumble around on a website for like Nature or something, trying to find a paper, but I figured I'd cut all that crap out and just start here with an interesting paper I found on my own time off screen. So you can maybe see why I picked out this paper. It's about sperm, and I figured, people on the internet are fairly mature, so this is kind of probably falls into a topic that might grab a lot of people's attention. So looks like these researchers, whoever they were, sequenced a ton of sperm genomes to try to figure out what they learned. So start off here with loads. Nice diagram of looks like their sequencing method. And these cute spermies with different colors. Tremendous sperm fluoresce somehow. I assume they egg making agents. Okay, so somehow trick the sperms into thinking they fertilized an egg so that they got the DNA from them, and then form some kind of droplets. Okay, so this is a lot like single cell sequencing methods. From what I know about single cell sequencing, oftentimes single cells end up secluded into these little droplets with barcoded beads. And then they formed a library for their sequencing. Okay, pretty straightforward. This is a Nature paper, so it's going to have at least 50 figures, and each figure will have at least 50 sub-figures, like 50 panels, I guess. But that's okay. Normally the figures look pretty cool. Oh man, this one looks really cool. Loads to full screen. Okay, so here they're looking at variation crossover positioning. Okay, so have some kind of frequency of crossovers on the y-axis and then position on the chromosome. So it looks like there's like a couple hotspots for crossovers on chromosomes. Chromosome 5 has like 3 hotspots where there are a lot of crossovers. Chromosome 3 has like 2 hotspots. That's interesting. Here we have proportion of cells versus proportion of crossovers. So most distal chromosomal zones, geez, say that 1,000 times fast. So I guess distal chromosomal zones is regions at the ends of the chromosome, perhaps? Portion of crossovers in distal zones. I wonder what they defined as distal. Distal is a relative term. Distal relative to what? Crossovers per cell. Oh man. Some cells had like 28 crossovers. That's quite a lot. Portion of two crossover chromosomes. Crossover separation per cell. Phenotype, two crossover separation. Some cool box plots. These little point clouds, little diamonds. These little clouds, they look like chess pieces almost, like a pawn. Or maybe what do you call it? Like a castle. That's obviously not the important part here, but it's what catches my eye. Crossover in cell. Okay, so they're comparing crossovers in somatic cells or body cells versus sperm cells, I'm guessing. Well, that doesn't make much sense, I don't think. Somatic cells normally have crossover events. Two crossover separation type to the same donor sperm. Looks like there's not much variation between these three groups. Decile. Okay, so those are like they split some kind of distribution into tenths. And here they're showing just a few of those tenths. This is my guess. Interesting. I'm already a little lost. Let's see if we can move some around. I'm not sure if I'll look at all the figures because these figures tend to be pretty long, but their figures are often pretty interesting. The rest of these figures are just like supplemental figures. So, okay, this is looking pretty neat. Aneuploidy and sperm. Oh, okay. Interesting. Aneuploidy. Oh, this is a we'll get to later. Aneuploidy. If you're not familiar with the term, pull up the Wikipedia page. Essentially refers to a cell that has an abnormal number of chromosomes. Picture like humans, for example, they have 46 chromosomes when everything goes well, that is, but sometimes something goes wrong during development. A person can end up having more than 46 chromosomes or fewer than 46 chromosomes, and states like that are referred to as aneuploidy. So, like in this picture right here, this is what's called a karyotype of chromosomes, where for an individual cell, each cell has 2 copies of every chromosome. One copy comes from mom and one copy comes from dad. So in this state, this cell right here has 3 copies of chromosome 1, or sorry, chromosome 21, instead of 2. So that cell is referred to as an aneuploid, and in this case, having a 3rd copy of chromosome 21 endows a person with Down syndrome. So these guys are looking at abnormal chromosome numbers from 20 different people. focusing on just a couple different chromosomes, chromosome 9, 18, and 3, looks like. Okay, this may be an aneuploidy stuff. Yeah, here they have like copy number of regions versus chromosome position. It's the peaks and troughs along the length of the chromosome. Well, not much variation on chromosome 18 at all. It's a very uninteresting flat line. And chromosome 2, though, it's pretty noisy. Chromosome 3, this is what the stock market looks like. Nice booms and busts like that. And then it's kind of like my wealth, really, just to stay steady. It doesn't go up, doesn't go down. Let's see here. Go on to the next one. Gain frequency per cell. Loss frequency per cell. And they zoom in on the top corner. So I guess they have, looks like they have one. Weird, they have these like crosshairs as data points. Those might be error bars. They're probably error bars. It looks like for most of the chromosomes, the frequency of loss is greater than the frequency of gain. Loss and gain of what? I'm not sure. But the loss points lie pretty heavily on one side of the dotted line. Same for this plot right here. They're comparing chromosomes versus donors. They go right here, versus donors. Oh. Meiosis 2 gain frequency. Okay, so I'm guessing what's happening here is that the frequency at which cells gain an extra chromosome 22 is shown here on the y-axis by meiosis 2. Then I guess the frequency of cells gaining an extra chromosome during meiosis 1 is on the x-axis. For review, get a nice plot of meiosis going. More or less thirsty, I drink water. This is like the stock price of Bitcoin. It's a big spike right here. Well, it may have crashed. I don't really know much about Bitcoin. I'm a pretty sheltered guy. Copy number versus position. It's pretty stable along the length of the chromosome, I guess. Varies a little bit between 2 and 3. That's pretty different for chromosome 15. There's like an entire missing region right here for chromosome 15, at least in this particular cell. Maybe something similar is going on here too. It's like this humongous chunk right here, just no copy number variation. So I assume that's just like a missing region of the chromosome or some kind of chromosome abnormality. So it looks like cells or sperm cells more often lose a chromosome than gain a chromosome, perhaps. That's what I'm kind of getting so far. Pretty interesting. And sperm seek. You know, I've heard of I know that researchers, when I took an intro genetics course, I learned about methods for performing PCR, polymerase chain reaction on single sperm cells, but um, I never heard of something like this, sequencing single sperm cells. Seems way more complicated than what I learned about. I don't know. Seems like because you can just already amplify a single sperm cell, the DNA of a single sperm. I don't see much of a reason to go through this single cell sequencing method. I'm sure there are, I'm sure there are other benefits. See, do any of these other figures look interesting? Nice line plots. These are like some cute sperm diagrams. Let's go on this one. This paper is a little older, came out in July, and kind of a big splash in news recently. Was the entire human chromosome 2, and so I would come back to the paper and figure out what he did. Trying to learn more about chromosomes. It's definitely the most exciting area of biology now, I think. So much data to be mined, genomes. Let's try to figure out how to sequence the entire X chromosome. So I have some kind of map here of different regions on the chromosome. There are all the chromosomes here, except for the Y chromosome. Each region on the chromosome is marked out by these different colored regions. Looks like there's some sort of markers, or perhaps these are genes next to a chromosome. They're focusing on just a single gene or locus. CHM13 assembly. Never heard of CHM13. Bio-nano support for repeat structure. Sequence read depth versus. Okay, so before the polishing, they had a lot of variation in the depth of the sequencing, but then afterwards, did some kind of normalization to even a lot of it out. A coverage of about 30x. It doesn't seem like a lot to me. Read papers on plant genome sequencing, and it seems like much greater coverage is required to sequence plant genomes than genomes. And meiosis is still not loading. Kitty cat, I'm streaming. Can't we talk about this later? You're hungry. Oh, you're always hungry at this time. Don't worry. I'll feed you soon. Alright, so the next figure. Let's see here. Bring it up to full size. So it looks like they had some kind of novel assembly method. Allowed them going to complete the X chromosome sequence. So here they're focusing on just the centromere of the X chromosome. Mark off the little arm versus the larger arm. I always thought the P arm was the larger arm, the Q arm was the smaller arm of the chromosome. I guess I got that wrong. Maybe we could look it up real quick. Nah, we don't need a picture of meiosis anymore. You already know. Comes up. Medicine.net says I'm wrong, so oh well. Yeah, my cat agrees too. Just let's see here. So zoom in on the centromere. I guess that makes sense. I imagine the centromere is one of the more difficult parts of the chromosome to sequence. So I think centromeres have a lot of repetitive regions, repetitive structures that are repeats in general are very problematic for building genomes. So that's not too surprising there. Looks like there's showing overlaps here between different contigs for the centromere, and then those are collapsed down into one consensus. Interesting. And for whatever reason, they ran gel comparing two different sequences. Array size. I think these are two different methods of, say, PCR. I've never heard of ddPCR. CHM13, we saw that in the previous figure. These like different assembly methods, perhaps. Let's see here. Here it's showing different read lengths. Same here. I guess it's showing the relative frequencies of the different lengths. Don't know why they added a bunch of polka dots. And then they show another figure of variation in coverage depth. Same difference between the top and bottom figure, but it's not immediately obvious what it is. And then comparing spacing density between the X chromosome and something called DXZ1. Okay, and try to figure out what DXZ1 is from the caption here. So DXZ1 is some kind of array. Weird how the X chromosome has a lot of these other tiny peaks, as the DXZ1 has just one large peak. Let's see. Ooh. CpG methylation. It's always a hot topic. So CpG methylation. Let's go ahead and Get a nice Wikipedia page going for that. Wikipedia pages are generally pretty good. From what I remember, CPG sites are just regions in DNA. So you put one gene next to a cytosine on a given DNA strand, and regions like that are often have methyl groups added to them. In the context of gene regulation, those methyl groups tend to turn off a gene in the colloquial sense, prevent it from being expressed, prevent its information from being interpreted by the cell at a given time. Let's see if there's a nice picture here that shows it better. Yeah, so like this picture right here have a C building block next to a G building block, and regions like that tend to have methyl groups added to the C. I think pretty sure added to C. So it looks like here they focus on three different, the X chromosome. I guess these were three different regions that were especially hard to sequence, probably due to repeats or something of that nature. And comparing read depth to the amount of methylation at a given site. This is interesting. So, or like regions of high read depth associated with regions of low methylation or something. This huge drop off in methylation here, and then a slight rise in read depth. And then, so these are probably some kind of alignments, perhaps. Let's see here. Nanopore coverage. How cool is nanopore? Interesting. From methylated to an unmethylated region. Okay, that's a transition right there. So it looks like they had decent read coverage in these regions. Not sure what the difference is between the red areas and the blue areas. I feel like that's standard, but I'm not sure what it is. I know that for some reads, red denotes a read aligning to a forward strand, and blue denotes a read to aligning to a reverse strand. But yeah, I don't know. Anyway, looks like cool work. I used some looks like a novel ultra long sequencing method, nanopore sequencing, to complete the sequence of the X chromosome. I wonder, I mean, is this the first human chromosome to be completely sequenced? I feel like it's not, but I don't know. Maybe they, which chromosome will they take on next? I'm very surprised they were able to publish a paper on just one chromosome. Okay, so I guess this was the first human chromosome to be sequenced in its entirety. 3, 6, 8, 10. Okay, so like apply this technology to the small chromosomes first, assemble those, and then they're going to focus on the larger chromosomes, which will be harder to assemble, and ones with the uh, off-center centromeres. That's pretty cool. I always kind of wondered, like, when people talk about the human genome sequence, I always wonder, like, whose specific genome are they talking about? Because I'm pretty sure that, um, well, the human genome varies from person to person. So if you're trying to develop a reference human genome, like whose genome do you use as the reference? Um, it's an interesting question. I think what scientists currently do is that they sequence the genomes of many individuals, and then they have some amalgamation of the genomes of those individuals serve as the reference. I'm not entirely sure how that works, but um, yeah, pretty interesting though. Anyway, coming up on my 30 minutes, so I'm probably gonna take a break. Uh, if you're watching this in the future, thank you for spending some time with me, and have a good rest of your day. I think I'll stream again, perhaps this weekend, maybe tomorrow if I'm feeling up to it. Typically try to do uh, streams around 11 a.m. Eastern time, so we'll see how that works out. Anyways, bye.